Hello. Today I'd like to talk about the second part of the velocity and acceleration section. I want to take a small side trip and talk about differential equations just a little bit because they figure into the whole velocity and acceleration thing for the projectile problem. What I mean by a differential equation is an equation that takes some quantity, its rate of change or derivatives, the independent variable, and relates these three things in a certain way. As a very simple example of this sort of thing, this is a differential equation. Derivative of y with respect to x is 3x squared plus 2x. Naturally, this is easy to solve. Integrate both sides. On this side, we're looking for an antiderivative for dy dx. We're looking for a function whose derivative is dy dx, so naturally that would be y. Strictly speaking, y plus a constant. I'll save the constants for the other side. An antiderivative for 3x squared is x cubed. An antiderivative for 2x is x squared. So y could be x cubed plus x squared, but because the derivative of a constant is 0, it could also be x cubed plus x squared plus a constant. C will be called the constant of integration as usual. If I give you additional information though, for example, if I tell you that when x is 1, y is supposed to be 4, if you put this into the solution that we just found, you can easily calculate the value of c to be 2, and in this case there is no unknown constant in the problem. For this problem, dy dx equals 3x squared plus 2x, and the additional initial condition that when x is 1, y is 4, you can state that the solution of interest is y equals x cubed plus x squared plus 2. You can do similar things if you have higher order derivatives. You could have the second derivative of y with respect to x equals 3x squared plus 1. In this case, as it turns out, you're going to need to know two facts. I could tell you the value of y at two different x values. That would be called a boundary value problem. Or I could tell you the value of y and the value of y prime at a same number. I'll use t equals 0 for that. And this would be a second order initial value problem. If you integrate it the first time, you'll find out that the derivative of y with respect to x has to be x cubed plus x plus a constant. However, since you know that when x is 0, you're supposed to get 3 for y prime, this lets you figure out what the c is. So dy dx is certainly got to be x cubed plus x plus 3. We're looking for what y is, though. We'll need an additional fact to get rid of the constant of integration to come, and luckily we have an additional fact that we haven't used yet. Integrating again, you find out that y has to be 1/4 x to the 4th plus 1/2 x squared plus 3x plus a constant. Strictly speaking, I should have used a different letter rather than c, as I've used that one previously. However, we've already found the value of that c, so hopefully there'll be no confusion. dy dx at t equals 0 told us the previous constant of integration. Now, when x is equal to 0, I'm supposed to get y equal 2. If you insert that into the formula for y that we just got, you immediately find out that the c has to be 2. So the function y of x that obeys the second order differential equation with the two conditions as stated is this function. All of this is relatively easy because it just boils down to doing an integration problem. Of course, things don't have to stay that nice. A differential equation that states the rate of change of y with respect to x is the same thing as 3 times x squared plus the value of y is a perfectly legitimate differential equation. If you try to write out the answer as we did before, you immediately see that you've got a problem. To figure out what the integral of 3x squared plus y with respect to x is, you would need to know what y is. But unfortunately, y is the thing that you're looking for. So this equation is true, but it's not particularly helpful to us. If you're interested in many methods of solving these kind of equations, we have courses in differential equations here at Austin Peay, and you could check those out. The textbook talks about projectile motion. This is motion in the Earth's gravitational field. The book doesn't explicitly state this, but this equation, the acceleration, the second derivative of the position vector with respect to time, equals 0, negative g, a constant. This is true only close to the surface of the Earth. If you move significant number of Earth radii upwards, then this equation is no longer valid. The book does everything in 2 dimensions, so we will as well. If we wanted to do fully 3-dimensional things, the second derivative of r would be 0 in the x direction, 0 in the y direction, and minus g in the z direction. G is a positive constant, the acceleration due to gravity. It is 32 feet per second squared, or 9.8 meters per second squared approximately. We integrate vector functions in the same way we differentiate them, one slot at a time. A purist might say we should put constants of integration into both slots. However, if we did that, we could just split the constant vector back out again at the end, so I won't bother doing that. The acceleration is vector 0, negative g. The acceleration is the second derivative of position, which is to say the first derivative of velocity. So dv dt is the vector 0, negative g. As within the simple things we looked at to start with, this is easy to deal with. V must be an antiderivative of vector function 0, negative g, which is easy to integrate. 0, negative gt plus some constant of integration, a vector constant of integration now. We need to figure out what the significance of that c value is. We'll presume that we start at t equals 0, and let's evaluate what the v vector is at that initial time value, at t equals 0. I'll have 0 in the first slot, negative g times 0 in the second slot, which is 0. So this first vector is the 0 vector. V evaluated at time 0 is the c vector. So I know what this constant of integration now is. It's the velocity vector at time t equals 0. For now, I'm just going to leave it written in this form. The velocity vector worked out to be this quantity. The velocity vector is the derivative of the position vector, so the position must be an antiderivative of the velocity vector. The position vector then is 0, comma, negative 1/2 gt squared, we integrated with respect to t, plus, this was a constant vector. Antiderivative for a constant vector is that constant vector times variable, which in this case is t, plus a vector of integration, constant vector of integration. I called it d this time just for variety. What is the significance of d? If we evaluate the position at the beginning of the situation, then this part evaluates to 0, so does that one. It turns out that the d vector is just the initial position vector. It's r evaluated at t equals 0. So we can summarize what we have figured out with the equation that's in the box. Now, since your textbook assumes that everything happens in the xy plane, various simplifying assumptions and notations have been made. Firstly, we're going to assume that at t equals 0, the object starts off directly above the origin. So the position at time 0 is 0i plus h times j. 0 would be the initial x-coordinate, h would be the initial y-coordinate. Secondly, because we have various descriptions of vectors in the plane, we're going to write v0, the initial velocity vector, as its magnitude times the cosine sine vector. In this number is a constant. It's the initial speed of the object. Theta is a constant. It's the initial angle of inclination of the object. Thirdly, they adopt a notation where no arrow v with a subscript 0 is the magnitude of the velocity vector at time t equals 0. Using these notations, the initial velocity vector is, in the first position, the initial speed cosine theta, and in the second, the initial speed times sine theta. If you take all of these little pieces and put them all together, r at time t is this plus this plus this. In the middle vector, the t is a number that multiplies the vector. I can bring its components inside and write this part as the initial speed times time times cosine of initial angle of inclination. This is v0 times t times sine theta. I have to add in the initial height and subtract away the effect due to gravity in the second slot. This number is the x-coordinate in terms of time, in terms of t. This is the y-coordinate in terms of time. As an example of this, let's imagine that we have an object that starts off at t equals 0, that is, 2 meters above the origin. At that time, it's given a speed of 100 meters per second. Its initial angle with respect to the positive x-axis is 37 degrees. I'd like to figure out where does it hit the ground and how fast is it going when it does so. Under these circumstances, the h in our formula would be 2, g would be 9.8, the initial speed is 100 meters per second, and the initial angle of inclination is 37 degrees. Given the facts that we know, insert them into our formula for r, and this would be a formula that gives you the position at any time t after the initial time. If you're going to write things in decimal, don't round. because rounding can throw your answer off quite a bit. So I figured out what 100 times cosine 37 degrees was, and I write all of the digits that my calculator gave me times t. In the second one, I had 2 plus 100 times sine 37 degrees, which turned out to be 60.181 some odd, all multiplied by t, minus 1/2 times g times t squared. 1/2 times 9.8 is 4.9. That's where the 4.9 t squared came from. If I wanted to write this in terms of x and y as being functions of t, x would be this first vector component, and y would be the second one. So we have split out the x and the y here. To say that the object has hit the ground means the same thing as its y-coordinate is equal to 0. So we're going to figure out, for this situation, at what t value is y 0. Notice that's not going to completely answer my question. The question was how far out or where does the thing hit the ground. We will still have to calculate the location. Writing down the equation y equals 0 in this case is the same as writing this equation down. This is a quadratic equation for variable t, so it should have two solutions. I used a calculator routine to solve this. There are two t values that work as usual. One of them is negative though, and I don't care about that one because the situation started at t equals 0 and then time moved forward from that. So this value means nothing important to me. The other one though, the positive value, is the t value bigger than 0 after the beginning of the situation, at which my object is going to be on the ground. Having determined the t value of interest, go back to the formula for x and insert the t value that we found, and you'll find out that the object started off 2 meters above the ground, had its initial velocity vector, magnitude 100, inclination 37 degrees. At some point it reached an altitude of 2 meters above the ground again, and then continued falling for another 2 meters in the vertical direction. The place where it hits the ground is x equals 983.5262592 meters. I don't really expect a measurement could be that accurate. I'm just not rounding any to prevent any kind of rounding errors. If I want to know how fast it's going, I need to know the magnitude of the velocity vector at the time at which the object hits the ground. If you differentiate the position function, you get the velocity vector. I then evaluate that at t equals the time of impact at t equals 12.315083. This is the velocity vector at the moment of impact. Vectors have both lengths and directions. To finish answering my question, I need to know the magnitude of this vector. That's going to be the speed with which the object hits the ground. So again, not rounding, being careful about things getting squared correctly. We found out that the speed of impact is 100.1958106 meters per second. Notice that that's a little bit more than 100 meters per second. As the object left its initial position, it had speed 100 meters per second. It lost speed as it went upwards, then it began to gain speed. At the moment where it was 2 meters off the ground here, we could check it, but the speed is 100 meters per second at that point. But then the object continued to fall for just a little bit, picking up a small amount of additional speed. These are the main points that I wanted to make in regard to projectile motion in the way that it's done in the textbook. I split this up into 2 pieces in the hope that it wouldn't just bury people under a mass of material. I hope that this is clear enough that everyone easily understands it. We continue with Snowpocalypse number 2, but hopefully I'll see you again soon.